Hi and welcome to another lesson about memory. Today we are going to talk about basic memory instructions, or basically how to deal with memory using our assembly instructions. Objectives of this lesson. We will learn about the following subject: how to access memory using the x86 instructions, how to count addresses properly, how to store a D-word in memory, or basically which byte comes first. We will learn about advanced addressing with the bracket syntax, and also about some limitations when accessing memory in the x86 processor. The bracket syntax. The brackets are the usual syntax for accessing memory. So whenever memory is being accessed, you are going to identify it using the brackets. As an example, X inside those brackets represents the contents of the cell in address X. This is the map of the memory, this table. And the upper row represents addresses and the lower row represents the contents of the cell corresponds to the address. Then for example here, the cell at address X contains the byte 25 in base 16. The brackets could be used with most of the instructions that we have learned about so far. There are some limitations, but for the most part, you can always try. You can always try to put the brackets and see if the assembler manages to assemble your instruction. Let's look at some examples. The first example, add EAX, D-word, ECX. This instruction goes to the address pointed by ECX and takes 4 bytes from that address and adds them to EAX. The D-word operator asks for 4 bytes. If we didn't specify the amount of bytes that we wanted, the assembler will not always be able to guess it. It will sometimes be able to guess it, but most of the time the assembler will not like it, that you don't specify how many bytes you want. Another example, move 0 extension EAX word sum mem. Sum mem could be, for example, a label inside your program, or maybe some constant, some numeric constant. So basically, this instruction just goes to address sum mem, and then it copies 2 bytes beginning from this address. It then extends those 2 bytes, a 0 extension, and copies them into EAX. Another example, neg D-word ESI. This instruction actually reads the memory and also changes the memory. It reads 4 bytes beginning from address ESI as one D-word, and then it performs 2's complement over this D-word and stores it back into this location, into address ESI. Another example, XOR D-word EDI ESI. This instruction changes the memory in location EDI. Basically, it takes the contents of the memory in address EDI, it reads 4 bytes as one D-word, then it performs XOR with the contents of ESI, and it stores the results back into address EDI. In fact, it stores 4 bytes. The first one in location EDI, the second one in location EDI plus 1, and so on. Addressing. The byte, which consists of 8 bits, is the basic quantity regarding x86 memory management. You cannot read or write less than 1 byte. And also, all the addresses actually count bytes. You can use the D-word, word, or byte operators to specify the wanted size of memory for read or write. And if you don't specify, the assembler will usually complain. Sometimes you will be lucky and the assembler won't complain, but I do hope that it will complain, because it is pretty important to write how much memory you want to read or write, in my opinion at least. Let's look at some examples. Move EAX 3. This instruction will just not assemble. The FASEM assembler will not assemble this instruction. And I think FASEM is right. It cannot know whether you want to copy one byte, maybe the byte 3, or maybe one word, the word 3, or maybe one D word. Maybe you even want to copy a quad word, which is 8 bytes. Nobody knows. So you have to specify what you want. Let's look at some proper examples. Move dword EAX 3. This example copies the dword 3 into address EAX. Basically, it is going to change the bytes in addresses EAX, EAX plus 1, EAX plus 2, and EAX plus 3. Another example. Add word EAX 3. Here we add the word 3 to the word in address EAX. Another example, sub byte EAX 3. Here we subtract the byte 3 from the byte in address EAX, and we store the result in address EAX. Endianness, or maybe endiannity. It depends how you want to call it. There is more than one way to store a D word or 4 bytes in memory. There is also more than one way to store a word in memory, which is 2 bytes. So we have to pick a direction or a convention. In x86 processors, when a D word is stored to memory, the least significant byte is stored in the lowest address. This is called the little endian or the Intel convention. In some other processors, the D word is stored such that the least significant byte is stored in the highest address. This is called the big endian convention. Let's look at an example of storing the D word 1, 2, 3, 4, 5, 6, 7, 8 in memory. I chose this D word because it is easier to see what happens. So we begin with the little endian, which is the x86 convention. This is how D words are actually going to be stored in your program. Maybe unexpectedly, it will be stored in this direction. Just as it says here, the least significant byte, which is 78, is going to be stored in the lowest address, which is this address, the lowest one. Maybe a bit unexpected, but don't worry, you will get used to it. It has some major advantages. It also has some disadvantages, like everything in life. And don't worry, you will be able to manage with it. Let's look at the other way, big endian. There are some processors that use this convention. Maybe one day you are going to meet one of those processors. So it is a good idea to know also about this convention. In the big endian convention, the number is going to be stored this way. So the least significant byte is going to be stored in the highest address. And basically this is the difference. You will also see that in the x86 processor, whenever you store a word in memory, it will also be stored such that the least significant byte is stored in the lowest address. So you can remember this line as a guideline whenever you are dealing with memory in the x86 architecture. Let's look at an example. And this example is about the following idea. The assembler cannot guess your perception about memory. Also, the processor cannot guess your perception about memory. Let's assume that you want to store 3 consecutive D words in memory. This might be your first attempt if you have never used memory at all in any of your programs. Let's look at this program. It has this data section which contains this label, my D words, which points to 3 D words of the value 0. And then we have the text section, which actually contains the code that is going to run. First, we move the label MyDwords into ESI. Now ESI points to the location in the memory where the 3 dwords begin. And then initially we move 1 into this dword. Let's actually try to understand what is going to happen here. This is the representation of the memory relative to the MyDwords label. So actually you can assume that the MyDwords label begins here. And let's see what happens. First we move MyDwords into ESI, which means that ESI is going to point here. By the way, all this memory is initialized with zeros. That is because we wrote 0 here. Now initially we move 1 into the memory in location ESI, the dword in location ESI, which means that we are going to put 1 in this dword, which is spanned from address of offset 0 to offset 3. And this is what the result should look like. I remind you that because of the endianity, the 1 is going to be on the left and not on the right. Now we increase ESI because we want to store the next dword. But something strange happened here. Instead of moving the arrow to this location, to 4, the arrow moved only 1 to the right, which is a mistake. We didn't want this to happen. But let's just look what is going to happen with this mistake. Next, we move 2 into the location ESI in memory. And this is what happens. We store a dword into the location of 1, which actually overwrites these offsets, 1, 2, 3, and 4. Next, we increase ESI. And finally, we store the dword 3 into the location pointed by ESI. And we get this result. As we have already said, this is not what we wanted. We actually wanted to store 3 consecutive dwords. And here we had a problem. The dwords have overridden each other. That's why we didn't even get to these locations in memory. And we have to fix it. The problem here was that we thought about MyDwords as an array of 3 elements. This is how a human being sees it. A human being would say, MyDwords is an array of 3 dwords, which contains 3 dwords of value 0. The first one is 0, second is 0, third one is 0. However, the processor doesn't care. You just said increase ESI by 1, and the processor increases ESI by 1. It doesn't care what you think about MyDwords. Also, the assembler doesn't care. This is what you requested, and this is what you get. We can fix it. This is the correct way to do it. Instead of increasing by 1, like this, we are going to add 4 to ESI. And this time, the first dword is going to be stored here. The next one is going to be stored here from offsets 4 to offset 7. And the third dword is going to be stored from offset 8 to offset B. Remember, x86 addresses always count bytes. They don't count words or dwords. They count bytes. This is very important. Advanced addressing. You could put more complicated expressions inside brackets, which is really non-trivial. Some examples. Move dword ECX plus 1, 3. This is going to store the dword 3 in the address ECX plus 1. In fact, it is going to store, as we have learned from the endianity slide, it is going to store the byte 3 in location ECX plus 1. the byte 0 in location ECX plus 2, the byte 0 in location ECX plus 3, and the byte 0 in location ECX plus 4. This is actually what is going to happen. Another example, sub byte ECX plus ESI 3. This is going to subtract 3 from the byte at this address, ECX plus ESI. And these are other examples of things that you can do. This is going to negate the word at this address, where, by the way, star means multiplication. So the address here is ECX plus ESI times 2. This is calculated first, and only then the addition is calculated, just as you would expect. Another example which is really advanced, add the word ECX plus ESI times 2 plus 3, 4. You might be surprised because this is just a processor, and maybe you didn't expect that the processor can understand this kind of complexity. Well, it does. This is one of the great features, and maybe some people usually complain about it with the x86 processor. It can get pretty complicated, but it gives you much power. You can do really amazing things with those instructions that you have already learned, just by using some interesting addressing ideas. The bracket syntax gives you much power as an assembly program. However, there is a limit to the possible complexity. You can't put anything that you want here. Why is that? Because those instructions are encoded somehow. You probably remember that the processor doesn't read text, it reads numbers. So there is a special encoding for each of those. And probably, as you can guess, this instruction, for example, has a pretty long encoding. And there is a limit. You can't encode anything. The options are pretty much fixed. So, for example, if you try to do crazy things, the instructions will just not assemble. For example, those two will not assemble. Move the word ECX plus ESI plus EDI 3. This one will not assemble because you use 3 registers. And usually you can only use 2, maximum of 2 registers. Another example which is not going to work, which will not assemble, is move the word ECX times 177. It looks like you have much freedom here, but basically you can't put so many different numbers. I think that some small numbers are going to work, but not every number. For example, this number is not going to work. You might be wondering, how can you know if something is going to assemble or not assemble? I recommend that you just check it. Just try to assemble it. I think it's a bad idea to try to remember everything by heart. You can know that basically those things are going to assemble. Basically, maximum of 2 registers, you can multiply one of them, and you can add some small number. And the multiplication should be by some small number. These are basically the rules. There are always some strange exceptions. I think maybe multiplication by 7 is not going to work. I'm not sure about it. This is up to you. You should check it and see what works.
The memory-to-memory limitation. The following instructions will not work. In fact, they will even not assemble. Let's discuss the first one. Move the word at location EAX, the word at location EDX. This instruction tries to take the word from location EDX in memory and store this D word in location EAX in memory. As I just stated, this will not assemble. This is because the x86 processor has some kind of limitation with its ability to access many memory locations at the same time. Generally speaking, the x86 processor can only handle one memory access per instruction. In this instruction, we can see that we have 2 memory accesses. This is the first one, and this is the second one. We try at the same time to read from location EDX in memory and to write to location EAX in memory. And this is not possible with one move instruction. If, for example, we really wanted to move the D word from location EDX in memory to location EAX in memory, we would have to use more than one instruction. Maybe, for example, we could first take the value from location EDX in memory and store it in some temporary register. Maybe, for example, the register ECX. Then we could use another move instruction to move the contents of the register ECX into location EAX in memory. Another example to instruction that will not assemble from the same reason is this: XOR dword EAX, dword ECX. This instruction will not assemble of exactly the same reason. We are trying to access two memory locations at the same time. Here we try to read from this location, ECX, and then read and finally write to this location, EAX. And this is not possible. Generally, if you try to do this, your program will not assemble. The assembler will complain that this kind of instruction is not possible to encode. As a rule of thumb, we can summarize this by saying that x86 can handle at most one memory argument at a time. You should know that there are exceptions. This is kind of an historic hardware limitation. There are processors today that are able to do these kind of things. I'm pretty sure that the engineers that create the x86 processors would be able to do this too these days. But maybe as some kind of backwards compatibility feature, or maybe some backwards compatibility design limitation, it is not possible to do these kind of things. In the future, we are going to see a few instructions that are able to do these kind of things, that are able to access two memory locations at a time. But these are kind of special instructions. You cannot do it with the move instruction. Let's wrap up this lesson. We first seen that brackets are the generic syntax for memory access in x86 assembly. Almost always, whenever you want to access memory, you will have to use the brackets or the brackets syntax in some way. There are other special instructions to access memory, but usually you are going to use the brackets syntax. The next thing that we have seen is that addresses count bytes, and let me remind you what that means. Even if you think about your memory as a bunch of D words, if you try to take an address and increase it by 1, the processor will understand that you want to move on to the next byte and not to the next D word. You have to remember this one. Many higher level programmers confuse this. Maybe, for example, if you come from the C programming language, in the C programming language, if you take a pointer and you increase it by 1, you get to the next element, not to the next byte. For example, if you have an array of D words in the C programming language and you increase your pointer by 1, you will get to the next D word. This is not how it works in assembly language. In assembly language, addresses count bytes and only bytes. If you increase an address by 1, you will move on to the next byte. Next, we've seen endianity. We've seen that the x86 architecture uses the little endian convention, where the least significant byte is stored always in the lowest address. If you store a D word to memory, don't be surprised if the bytes are stored in the opposite direction from what you have expected. We saw that the brackets support advanced addressing, which means that we can put pretty complex expressions inside the brackets. At the same time though, you have to remember that the bracket syntax has its limits. You cannot put any expression that you want inside the brackets. Only some expressions will work. If you are not sure, you can always try to assemble your program and see if the assembly passes. Finally, we have seen the memory-to-memory limitation. In most instructions in x86 processors, it is not possible to copy memory-to-memory directly. Or basically, it is not possible to access two memory locations at the same time, using one x86 instruction. There are exceptions, but generally this is a rule to remember. See you on the next lesson.